Now, we move on to the next data set, which is a fairly large data set. It's a data set downloaded from an academic article database. And after I downloaded, I cleaned it first. I lemmatized, I removed stopping words, I turn them into lower pieces, break them into words, and then put them together, removing all the words that do not have actual meanings. Those stop words, those stopping words, like to, with, so, maybe so, and these words. Right, let's take a look at the high level of it. It has more than 10,000 rows. The critical column is going to be the abstract, and this is a column with long strings. I have prepared the strings, and then they look like this. These are prepared version of an actual abstract of a journal paper. This is a psychology database, I think. So you would see things like psychiatric, emotion, attitude, disorder, social, something like this. But I also added the what do you call it? These lemmatized these. So the functions of the words in the sentence, the point of the POS tags. These are the POS tags: verb, adjectives, noun. These tags for linguistic purposes. Sometimes these do add value in analyzing the analyzing the hyperdimensional spaces of the language, especially before the GPT era of the text mining. Right, just a little background. Now, the utilities we're going to be using is count vectorizer LDA model from sklearn. So let's import that. We're going to use a little utility here. It's tokenizer. It's a simple tokenizer where it's simply split by white spaces. So, mostly spaces, or maybe tabs are part of the white spaces as well. So it's a, smaller version, lighter version of the tokenizer. It will replace the native tokenizer by the package to speed up the process, and also to, remove other possibilities. All right, we'll move on to the next question. With the data set, with the column abstract prepared, now we need to model the vocabularies. We need to retain a set of features and discard the other features that happen too often across the journal articles. That's why the max features is set to something that's not too large. When you have too many terms in your analysis that is shared across the document, you end up not getting any meaningful results because the terms are too frequent. It doesn't indicate any uniqueness to the specific article that uses that term. So that's why we limit our attention to only a subset of the terms that happen less frequently across the documents. So you've learned the background by reading and practicing, so I'm not going to go too much depth in here. We're going to try to solve this problem. So with the count vectorizer, define it and then process the data and then create the TF. Now, TF is one of the 3 or 4 matrices that we're dealing with as a new construct, the new data structures here. I'm going to summarize all of them at a higher level. For now, we solve the problem here, and then we come back to summarize the different terms and different data structures. Term frequency here is also, we call it feature vectors. This is a matrix where you have the as many rows as the data set, which means here the data set is the journal or the journal articles. You have as many rows as the journal articles in the original data set. The columns, each column is a vector which represents a feature. So it's called, feature vectorizer, where you have a bunch of vectors representing features one by one. And then the values of this matrix represents the number of times that the feature appears in the journal article abstract. So that's the meaning of it. One of the questions down there asks you what it means. Okay, the way you derive the term frequency table is the 2 steps here. So the first step, you create an instance. You use the count vectorizer, specify the options, and then you create an object, create an object instance. Assign it to count as the question asks. Or the question didn't ask exactly, but you can call it count, you can call it anything you want, or table. But this provides an algorithm to archive all the unique terms and then discard anything that is more appearing more often across the documents. So count vectorizer with the parameters, the tokenizer is the one that we provide. My tokenizer specify the document frequency maximum level. Here it says 40%, and the number of the features. Yeah. The maximum number of terms that we want to retain as for analysis is 500. Now, once you have the count, now you're ready to fit that to the data set and analyze the data. So once you have count, and it's a transformer actually. So it's not a transformer in the sense of ChatGPT, but it's a transformer in the sense of the sklearn or the data processing, pre-processing transformer. You fit that into the data set, the DF, the DF1, DF academic, abstract, prepared. And once you fit the data, you assign it to TF. TF is a sparse matrix where you have quite a lot of zeros because some of the terms are not used at all. And since we're only retaining the less frequent words, the unique words, it's going to have a lot of zeros here. Now, when I run it, I'm having a error, and can anybody help me to debug? It says something is here. I don't see any issues. What do you think is the issue? Invalid syntax. What do you think is going on? Emily?
Is it the percent sign? It would have to be like decimal instead.
Yeah. Yes, yes, decimal will be able to solve it. But why not percentage? I thought percentage is also numeric. This part is kind of like a blind spot in Python in general. Here, I mean, specifically to, I'll talk about the percentage sign in a little bit, but here, the maxDF actually takes two kinds of data types. You can either provide a decimal, which then has to be smaller than 1. It has to be a percentage, decimal, which means the percentage of, why do I don't know, I have a student that is requesting access. A decimal, which specifies the percentage of all the unique terms that are found in this course to be retained. Sorry, the document frequency specifies the maximum number of the maximum percentage of the different documents, which means the journal entries, the journal abstracts. The maximum percentage of times that a term can appear in the different documents. If it goes over this threshold, the term is happening too often across the data set, which will be excluded, and then it doesn't meet the criteria. So for a decimal that does that. Alternatively, you can provide an integer, which is straightforward. This is the maximum number of documents that the term can appear. If it's over this number, then it will be excluded. So, considering that we have 10,000 rows, 0.4 is fairly large, almost half of the data set, which is 5,000. It's not as many as 5,000, but 4,000 something. But if I use 40, then it's a very small number. It's not going to retain many features. Could be just hundreds of features, maybe 100 or so. Because these are truly unique words that only appear in 40 or fewer articles, abstracts. These are very unique words, very peculiar words. So both are fine. This is not going to create an error. It's going to run. The warning, you can ignore that for now. With 40 here, just only going to, I don't think I don't think it should have to find this many, but we can take a look that maybe there are many zeros or empty values there. But with 40, it lowers I mean, it increases the bar, actually. It lowers the threshold very much. But the problem with percentage here is that percentage itself is a reserved symbol in Python. So whenever you have a percentage, it in a coding style, it's going to mean an operand. It's going to be it means taking the module. It's a module operand where you calculate the remainder of two numbers. So if you take the module between 10 and 2, it's going to calculate the remainder of this calculation, which means 0, because 10 is evenly divided by 2. But if you try to calculate the remainder of 10 by 3, you get 1 as the remainder. So that is a reserve symbol. You cannot use 10% as a decimal in any scenario in Python. It's not going to work. So just remember that. And if you want to have a decimal that's sufficient, or with or without 0, it's literally the same. Run that again. The warning disappears because it has warned before. It's only going to warn it once. It doesn't mean there's no warning. But anyway, the warning is saying, because I provided my own tokenizer, it's not going to use the native one. That's the only warning that it says. Once I have that, do that. Okay. So that solves question 5. And with that, we're going to print out something here and show a little bit of tutorial. The original. This is showing the original abstract and the pre-processed text in the dataset. I've shown this before. This is the processed string of the abstract. This is processed based on this actual abstract that's, published in a journal article. You can, if you're interested, you can read it. There are quite many special terms: avoidant personality disorder, APD, generalized social phobia, GSP. As is clear, this is quite psychology and psychiatry focused. APA is American Psychological Association. Anyway, so let's think about a scenario where there's a task that you want to achieve. With the TF, now think about TF again. TF is the term frequency. The frequency is the terms in the document, right? So it retains the number of rows, the same number of rows as the original data set. And the original data set is the journal article database. TF describes how many times a certain term indicated by the column appears or is counted in a certain abstract, which is indexed by the row. So now you have a way to find out what are some of the words that are that appear the most number of times, that appear most often, that is mentioned more often than other words in a particular abstract. Think of the first entry in the data set. Or think about this this abstract. In this abstract, what are the words that are mentioned the most number of times? You can use TF to answer this question. You can define the top words, essentially. If you want top 5 words, you can get top 5 words. If you want top 10 words, you can get top 10 words. You can get the number of times that each of these top words appear in this entry, and you can look up what exactly are these words, or what are the indexes of these words in the TF table. So this tutorial here, which is not provided as a challenge or question, but provided as a tutorial, I recommend that you read through the process to understand the logic flow and the techniques that are used. I'm going to talk a little bit about these. So here we want to get 5 terms that appear most frequently, the top 5 words. Okay, we take the first row, which is delivered here. I think the first row is this prepared abstract chunk of text. What words are the top words that appear most often? I don't know if anybody can figure it out by just looking at this. I certainly cannot, because I get dizzy by looking at these. So better resort to computers. So here's the process. You want to first identify the 5 biggest numbers in TF in the first row, because the numbers in this matrix indicates number of times each term appears or are found in this entry. So you find the max 5 numbers in the first row, you are in the game. Therefore you take the first row of the TF matrix, but before you're able to get the numbers, you need to convert it to array, because it's a sparse matrix. It's not going to give you the actual content before you turn it into an array with actual values. So you convert that and then take the first row. Once you have the first row indexed by 0, the first row, once you have that, you have an array. It's like a list. You want to find out which are the 5 biggest numbers, but you don't just want the numbers, you want the positions of those numbers. That's why you use arc sort, and then take the last 5. So sort alone means sorting the values. If you simply use sort, you get a sorted list of actual values, but you don't at this point, you don't actually care about the values, but you care about the positions of those values. So that's why you use arc sort, which sorts the value and remembers the positions originally. Once you do that, you take the last 5, because it's sorting ascendingly. You take the last 5 to get the highest 5, the position of the largest 5 values, and then you use this trick to reverse the order. This is all the list slicing tricks. Once simply you remember. Once you have these, following the logic, doing all of these operations, what you get are the index values of the top 5 words in a descending order. So you run that, you get these numbers. These are not the number of times the terms appear in there, because there are only 100 words here, or maybe 200. It's not going to be thousands. These are the positions of the top words in TF table, the column index. But once you have the column index, you're going to be able to do a few things. You can go back to the first row, and then based on these indexes, you can get the values of this TF. Now, what are these values? These are the frequencies, because it's term frequency table. You get the frequencies. So if you do that, you will get the number of times that the top terms are found in the first entry. 652. The top words are found 6 times. It's a clear winner here. And can you, intuitively and quickly guess which words are found 6 times in this abstract? All right, you give up. I do. I also give up. So why don't we, find out? How do you find out what are these words? You use the indices. These indices are preserved indices of the count object that the vectorizer object that we fit into the data. It maintains a dictionary of the indices and the actual terms from the data. So by using the dictionary and these indices, we can find out the values. To do that, we first need to get the map, the dictionary here. So here is the correction that you will need to do. Originally, the method here is called get feature names. You would need to add _out because it was updated in sometime last year around this time. Once you fix that, and then there are quite a few other places that you need to use this utility. Make sure you use get feature names out to do that. So once you fix that, you can copy and paste in other places. So fix that, we get the feature names. The feature names here is a second matrix that's important to us. Or maybe not a matrix, it's a lower dimension. It's 2 dimensions. I mean, it's 1 dimensional. Feature names is like a list or a dictionary where you have the indexes of the term and the actual term itself. Once you have that, you're going to provide the index and then it will return the word. Now, because we have 5 words, instead of printing one by one, we can use something that's called list comprehension. List comprehension. You can take notes, search in let me type out, search in Google, and then learn by yourself what list comprehension is. Okay, right. I'll leave it to you to self-acquire the skills. Essentially, you put list comprehension in a pair of square brackets. It will construct a list based on a pattern, based on a for loop, or more than a for loop. It can be nested for loops, but essentially it's a loop. So here, for I that iterates through the indexes, the 5 indexes following this order, this is descending order. For I that iterates through these indexes, I use that to extract the term. 5 terms are extracted, put them into a list. And once I have that, I glue the list items into a long string separated by comma. This is using the string.join function. And then I have a long string that lists 5 terms in descending order of their top word status. And then I print that. You'll see these. Right? These are the terms that happen the most. GSP and APD are the special terms that we see. And actually, it's pretty, it's pretty accurate. These are the topics, they're the actual domain knowledge of this article. That's why they are the top words. Alternatively, we have these POS tags, which doesn't, which impedes the understanding a little bit. But you can tweak the code a little bit to remove those tags by tweaking the list comprehension inside of it. Every time you extract a word, you also leverage the string methods by splitting them using delimiter and only pick first of the two. Because every time it's a pair, once you split them, you only retain the first part, and discard the POS tag. Once you do that, you'll have this. But this answers the question. But I do have a question for you. If you see the terms that are returned from the feature names based on the indexes, what do you see different from these feature names are the terms? And the terms are exactly these words or vocabularies or words from the original text. Little processed because this abstract is already processed. How are they different in terms of GSP/NN, APD/NN, different from the original data? How are they different? There's a GSP. There's a GSP again, APD. Are they different or the same? You'll notice that the terms returned by feature names, they have already been turned lower cases. Everything is lowercase. Whereas in the original text, the POS tags are uppercase. So when you apply the count vectorizer, even though my tokenizer only split them by using spaces but not changing cases, the default methods in in curating the vocabulary list, it's going to turn everything to lowercase to remove any possible duplications of terms just because the cases are different. So the lowercase Europe and the first letter capitalized Europe, they're going to be recognized as the same term. All right, so keep in mind about this use case, and later we will use it multiple times. Use at least the logic multiple times, maybe not the exact codes, but the techniques and the logic will be reused. All right, a little bit of conceptual question here. What is TF? What does that mean in this context? This is the journal article context. Explain, use your own words to explain what it is. So, now, anybody want to answer? Anybody want to use your own words to explain what TF is?
Term frequency, Professor.
Term frequency, and what does it mean exactly?
Actually,
the structure. Yes, go ahead.
It's like a matrix built from the column abstract prepared and contains a pre-proposed academic paper abstract.
Yes.
Each row represents one academic abstract, and each column represents one unique token, and each value in the matrix record is how many times that specific terms occurs in that particular abstract. That's it.
For times the token here in that abstract. Super. Great. Just to complete,
Yeah, thank you.
yeah, just to make it complete, the TF or term frequency table,
Yes.
also known as the feature vectors. By the way, it asks for feature vectors. So anyway, the two places switched. The feature vectors matrix or TF is there's a special term that we give it, is the bag of words representation. It's a way of modeling textual data, right? It's the bag of words representation of the academic abstract
Yeah.
column of the data set. Yeah. So there's another question about bag of words representation, and we'll get to it. Specifically, each row represents an abstract, that shares the same row index with the original data set. Each column represents a token whose column index is preserved uniquely and recorded in a feature names or it's in a dictionary or look at the actual term, right? Right. Just column indexes preserved and preserved chords and maps with the key in the dictionary. That's how you can use the key, the index, to look up the term, the value. The dictionary is a key value pair. And each value of the matrix represents the number of times the frequencies that the token appears in the abstract. Super. I think that's it. Any questions here? Great. So bag of words, what does that mean? If you have read the materials, I'm not going to go much into that. I'm just going to copy and paste here. Let's briefly go through. The bag of words means all the terms are lump sum. They are, typically sorted or are not sorted. Doesn't really matter. The ordering of the words in the original text is a context. It's a contextual information that gets lost with the bag of words representation. Which in other words, you say, I like you, you like me. These two sentences mean really very different things, but the context will get lost when you use the bag of words model. So that's the essential differences. Of course, our large language models are able to preserve the ordering of the words, which means it's much more capable to understand the meaning of our other human languages. That's why that's much more powerful than this LDA model, which was authored in the 90s, I think, or maybe even before 90s. Anyway, any questions here? All right, next we have two big problems to solve. We're going to train an LDA model. So the question asks you to train an LDA model with specific parameters. Because with LDA models, there is not a way to optimize the number of topics for a particular data set. It's a hyperparameter that you must choose by yourself. It's like the structure of a neural network. There's certainly no standard way to optimize and pick the best structure for a neural network. You have to start somewhere and then, adjust and try different things to see how they perform. And it's entirely data driven. Same thing with LDA model. The number of topics which means the number of dimensions of the term groupings, or, however you want to describe it, the number of dimensions there is entirely up to you. You can try different things and then come back and adjust and see the outcome. Here, the question specifies 20, so we're going to use 20 for the number of topics. And then assign the result to result LDA. And the process of running the LDA model is, again, 2 steps. You define the instance, and then you fit the object into the data, and then train the model. Right. So I copied the cell here. The 2 steps are laid out already for you, which is 2 lines. The first line is the first step, where you will create LDA objects by specifying the options. And for the LDA model, let me move up so that I can see the questions. For the LDA model, for the number of topics, so this is my variable. The topic, number of components and component. Number of components is the number of topics. Try to use the variable name and then define it up there instead of put 20 here, because sometimes you'll confuse yourself. You change here, but the model didn't change. The better practice is you define a variable and always use the variable name, and then you only have to change the variable itself when you want to change the model. Number of topics, specify the random state as the random state variable provided. And there's a learning method. We use batch gradient descent, batch processing. Okay, once you have the LDA, you can train a model with your data. And the data is, you use your term frequency table, X-rays, as a training material. And then both your LDA and your result of LDA will be the output. All right, this is going to take more than a minute. We'll have to sit back. Okay, while it runs, let me talk about the high-level concepts. There are several data objects. So now to kind of repeat a little bit. This is the TF structure. It has a number of rows corresponding to the document size or the number of documents, as with the original data set. And the number of columns refer to the number of terms reserved. And since we specify 5,000, it's going to be 5,000 in our case. Each column is a vector of terms. Each vector is not a vector of terms. Each column represents one term, but it counts the number of times that the term appears in each of the documents. The bag of words means the ordering of the words is lost. The meaning in the word order gets lost. This document frequency is used to, as a threshold to decide which terms are excluded. Now with the LDA, we have 3 or 4 data objects. Term frequency, we talked about it in detail. Then we have the concept of topic. Not yet. Congratulations. Yes. Where is it? So there is where is it? There's a concept that's topic. Now, what is a topic? Topic is a grouping of terms that share some commonalities in linguistic sense, based on empirical data. Computers doesn't necessarily, or certainly they don't know the similarity between favorite, like, love, and relationship with hate. Computer doesn't understand that, we do. However, computer can learn by the way we structure sentences and write documents. When we try to express some meaning, we use words in an orderly fashion whose patterns can be leveraged by computers. That's essentially what's happening behind LDA or any large language models. So the concept topic helps glue the other 2 concepts: document, which is the abstract in this case, and then term. So when you have the document and term, you have the TF, term frequency. When you have a matrix that connects document and topic, later you'll find that this is the document topic is the result LDA as the output of the training of LDA model. It's a matrix that has the same number of rows as the document, the original data set, but the number of columns that maps the number of topics. We specify 20. So this matrix has only 20 columns. And you have a third data object here, a third matrix, which is a topic terms, topic term or topics terms matrix, where the rows correspond to each of the topic. You have 20 topics, then you have 20 rows here. But the term here, it corresponds to the term frequency table. It has 5,000 columns. So with the three concepts here, you have three pairs, unique pairs. And then you have three objects. And one more data object, the fourth one, is the feature named dictionary. We will be using these four to play with the problems. Right? I think the training should be done, but one more time, recap. TF table, term frequency, feature vectors matrix. We have this dictionary or list. We have the result. This is document topic matrix, and then we have the components is the topic terms, the number of components. All right, and we'll come back to the notebook. So, okay, it took me 1 minute and 35 seconds to train it, and then we look at the result LDA. It's the document topic matrix, and then you confirm the number of rows and columns. All right, so that's the first part you have trained. I have trained an LDA model. And afterwards, by using the LDA components, which is the topic words matrix, you get the 20 topics, and for each topic, it has it tracks or it measures the weights, relative weights of each term related to this topic. Many of the words do not have close relationship or weights with this topic. It's going to have low weights. Only few words or terms of each topic would have high weights. So that's their relationship. Develop codes to extract and print top 10 terms. Again, top 10 terms with the highest weights. So top terms or most important terms. Does it mean frequency? Maybe, but this is slightly more complex than just the number of times or frequencies of the terms that appear in a document, which is simple counting. However, the topics are a concept. There's nothing that maps exactly to the topic. Topic are clustering of the words with high weights. It's a bridging concept. So there's nothing that maps it with it exactly in the data set. Then there's nothing that represents simple counting of the weights. The weights are relative affinity, if you will, between the terms and this higher level concept, topic. But however, the way you extract top words are similarly done with the term frequency table. So you can reuse the technique and the logic to do this task. You'll be using slightly different data objects to complete the task. The logic is the same. All right. The question asks you to only do the first 6 topics because you're going to do some interpretation here. Once you train the LDA, extract the top 10 terms of each topic, analyze these terms, and then try to come up with an interpretation of what this topic is trying to capture in the linguistic sense by using the top 10 terms. All right, so now there are 2 steps to solve this problem. Let's see. So this is question 8. Part 2. So 2 steps. I use a large little string as a comment. So step 1 is to get a few utility objects or utility variables. And the second step is a for loop. Within the for loop, there are 3 steps. There are 3 tasks. Within the for loop, you will need to loop through each line or loop through each topic, get the topic index. So this is a number of components here. The number of components, the components here object is the topic word matrix. So row is a topic. When you loop through the rows, you're looping through each topic and getting the words with their weights for each term. So once you have the array, you can get the indexes of the top words or top terms for that topic. And then with the indexes, you can get the actual term. Clean up, the tags or whatever in the data. So this is the general process we're going to do. Okay, so to get a few things, we need to get feature names again. If you did the previous question correctly, you don't have to repeat. But for completeness, I'm just going to repeat that here. Feature names, get feature names out. And then I also need to, the most important thing is the LDA, the number of components. This is the topic term matrix. And you can name it as topics terms is the components. And then also I like to, for any numbers that I am going to repeatedly use, I like to create a variable. So the top 10 words, the 10 is a parameter, is a variable, where you can quickly change the algorithm by changing this variable. So n top terms, meaning not how many top terms do I need to extract. In this case, it's 10, right? And then print the job. I need to have the F string because I need to include this to explain the number of terms. So the top n, the top number of the top terms of each topic are, right? And then begin the for loop, the second step. For, and here we're going to use the enumerate utility here. When you enumerate through a list or an array, we're going to get both the index and the content, which is nice. We need both. So when you enumerate through the topics term matrix, what you get is the index, and then you get the topic terms. Is the terms for this topic, or you can say all terms, or row terms. You're getting one row, one array, all the terms with their indexes. So, you pick the name, that is not too similar to the other names, but meaningful enough for you to recognize. I think there are some issues otherwise. Otherwise it's going to end it. So the way you do enumeration is like that. You specify two variables to accept it. So do some printing. This is topic number I, and then print the words. Now, we're here. We need to get the index of the top term for this topic by using the array, which is the row terms. How do we do that? Reflect back on the process that we extracted the top terms in each document. The tutorial here. Follow the same logic, use the same technique to do that. The only difference here would be that we're not dealing with sparse matrix anymore. I don't think we're dealing with sparse matrix anymore. The topic terms matrix are not sparse matrix, so we can simply extract the value instead of trying to do converting to array. That's the only difference. Other logics, the argument sort is getting the sorting them according to the value, but retain the index. Extract the tail 5, the largest 5, and then reverse order. All of these we can retain, right? So the end of the result of that is the index of the top terms. So that's the first step we're going to do in this task is say top, not topic, but top terms is the row terms, the order terms, where we do argument sort, take the tail 5, which is the largest, take their index, reverse it in descending order. But be careful, this is the index of the top term, not the top terms itself, but the index. We're getting the index of these. But once we have the index, we're ready to extract the actual terms. And then we use, again, we can use list comprehension, if you remember I talked about earlier. The way you do that is this. You can combine the 2 steps or do step 1, 2 little steps. I'm going to break it down to 2 little steps for you to see clearly. I'll retain the ring join as a second mini step. So using the index top terms and list comprehension, iterate through the index list to extract the terms and then put them in a list. So this list is going to be top terms list. There's one complication here. You don't want to, confound the 2 I's here. You don't want to, even though they may not interfere with each other, you don't want to have the possibility of that. So simply change it to something else, different subscript there. Be sure to change that as well. Okay. Then once you have the top terms, it's easy to glue them together by using a simple string. And then you can assign to the same variable. All right, once you have that, then you are ready to print. If you want to clean up the POS tags, then what you can do is in the list comprehension, be sure to do the split and then take the first component. And there you go. And then now you're ready to print the result. just the term. So easy, print the terms and then print some divider. Okay. Now let's take a look. So, but why 5? You know, we're taking top 10 terms, but better, we have a variable. So we simply use the variable instead of using arbitrary numbers which tend to make mistakes. Then I think everything's fine to do that. Okay, so this is the, it get all 20. The question only asks for 6. So you would slightly revise the code to only get 6. There's several ways to do that. Either you can limit the top 6 rows and then you only get 6. Or another way to do the same job is to limit the to put a qualifier on I and stop the for loop. If I is greater than 5, it means 0 to 5. If it's greater than 5, then it should abort. Could be break. Right. So you only get 6. All right. So this is the 2 steps of the coding task. Now, one last task that the question asks for is interpret. Read the top terms under each topic and try to come up with a brief description of the topic in your own language. Now, there's no perfect answer, so just try your best. If it helps, you can even get some help from large language models. I think that's nice. Okay, so now let's do some voluntary work here. Use whatever means you can get, all right? Your brain or your artificial brain. These are the top terms of each topic, and there may be some overlaps or level is the overlaps between the topics of the top words, but there are few overlaps, not even theory. There's only one theory. There may be some of the things that are repeated model, not really, which is good. You want separations because each of the topics should represent a different dimension. Now, who wants to go first? Based on these top words, what do you think the first topic is capturing? It can be a subdomain of the psychology literature. It can be a cluster of cases, psychiatric cases. It can be a methodology. I'm just throwing things out. So what does it look like? Self, person, state, trait, multiple situations, social behavior, case response. Who wants to go first? Anybody? It doesn't have to be long. It can be very short. It can be as good as a guess. Say it again. Oh. Anybody want to go or not?
Please, can you repeat the question?
The question is, based on the top terms identified for each topic, let's start with topic 0. Based on the top terms, these are the terms that has the highest weights for this topic. What is this topic capturing in terms of the meaning behind the words? What are the commonalities between the top words? If there's a theory, what kind of theory is there? If there's a methodology, what kind of methodology is there? If there's a subdomain of the psychology literature, what it is? Or it may not be as good as any of these that we saw, but what's the best that you can come up with?
I think based on this, I'm thinking the main topic is like personality, like because it's asking for like the traits and then like social behaviors and responses, and also like the person itself. So that's like a thought process.
But that's a lot of things. But I agree, it's not very clear what it is capturing. And let's just, throw it
We can
into
also give like personality
Gemini.
and learning performance also.
Could be. Although I wonder why personality didn't show up here. But yeah, it's not easy. It's pretty vague. This is, try to summarize the theme, maybe. Let's see. What does it do? The theme is interaction of self, social, situational factors on behavior. Really nice. I don't know what you think, but it's pretty creative. Something I definitely cannot think of myself. Self, person, state, and then remember, self. The word that appears on first is the heaviest weight terms. So self and person and state appears more important and relevant to this topic than the response and behavior, which this topic is more concerning about sort of the psychological state of, or could be personality state of the person right now. There may be multiple personalities, maybe. What does it say? Interaction with self, social, and situation. And situation, social, situational, self, and environment. So something between the self and the environment. I don't see much of the environment situation. Okay. So here, the way you answer this question is, topic 0. Based on student inputs just now, rather than the Gemini. Personality studies and behavior, if response, maybe something like that. There's definitely no perfect answer here. All right. So, but what we're trying to get at. The idea is that because the top terms are different across the topics, the themes that you come up with across the topics, they should at least be somewhat different. So they need to reflect what the terms actually represent. For instance, for topic number 1, although the trait is an overlap, but there are things a brain and cognitive, something here. The topic is reflecting a little bit more insight or a little bit more into the brain functions of the scientific domain
Like
about the
mental?
human body.
Something like
Say that again?
cognitive
Mental?
processes and learning performance like
Yeah,
that.
mental. Yeah, mental is one way to interpret it. So cognitive
Cognitive,
aspects,
we can read the cognitive processes, right?
cognitive and
Mental.
mental aspects
Right.
of human psychology, something like So I'm just curious what the Gemini will say. We'll just try that. The theme of the literature is exploring the human condition through love, power. I don't know where it gets it. This is a little too creative to me. But, even if it doesn't provide meaningful values, it provides some entertainment. Yes. Anyway, so you know what to do here for the sixth topic. Complete the interpretation of here. Do a little reflection instead of just copy and paste what AI tells you. I think this serves you much more benefits if you reflect on the task. All right, we have the last problem here. Now, this is going to apply the similar logic on the third data object here. We have done term frequency, which is the top words of the document. We have done the topic terms, which is the top words of each topic. And now we need to get the top words of the document by linking the topic in the middle, right? Instead of using simple frequencies, which may not be that useful, frequencies doesn't have to be reflecting the theme. Frequencies may just be a technical terminology used by the article. The idea here is two steps. You identify the most probable topic for an article based on in a statistical sense. Once you identify the topic for this article, you get the top 10 words for the topic. Then you put them together, you get the most important words, not necessarily most frequent words, but most important words for the most likely topic of the document. So these are putting the three concepts together in one task. So again, 2 or 3 steps, you can say three steps here for the two parts, but for the first part, it's going to be 2 steps again, very similar process. I'm going to copy and paste, save some time. So, get a few utilities. Under that, there's subtasks where you need to get the topic of I think there's a little breakdown in the process. To get the most probable topic, you might want to put that inside the loop. So again, after getting a few utility objects, you do a for loop. But here, the for loop is to loop through each article instead of each topic. And then once you loop through, But once you're in a specific topic, article, for each article, get the topic index for this article that's the most probable. Then once you have the topic, get the topic terms, get the row of topic terms. And then once you have the topic terms, get the index of the top terms for that topic. Once you have the index, you get the actual terms, clean up, and then print out. So you have one more step within the for loop because you need to extract to determine which topic are you focused on instead of looking through the topic blindly, right? This is the difference between this task and the task that precedes it. I think, and now the question only asks you to look at the first 5 journals because it's going to be, quite complex. You only look at the first 5 for loop, limit of 5 rows. The loop only goes through 5 rows. For each article, identify the topic, and then based on the topic, get the top 10 terms. So that part is the same. We define some utilities here. Feature names is again the LDA.get feature names out. The number of pop words on pop terms on the same, and the topics terms matrix is the components, and you also have the result LDA. Then result LDA, we don't have to do anything, and we'll just keep it there. So we already have it. The result LDA means the document topic. So the weight of the topics of each document. We actually, in fact, we're going to loop through the document topics matrix 5 rows. Then we don't have to, we simply have to identify the topic with the highest weight. Yeah. I think that works. Right, we already have the result LDA, that's the result LDA. So print the task. The top number of terms, the top terms for the most probable topic number that each extract is. All right, then start the for loop for the index, and this is the LDA result. Is the document topics, right? The document topics for I and document topics in enumerate result LBA. If you limit the first 5, that's that. I'll print the task. This is document or abstract index I. We need to determine the most probable topic first. For that, we can extract the maximum. So the topic ID, the top topic, the most likely topic, the ID for that is within the document topics. And then you want to get the index place of that topic. You use the argmax, and then take, right, argmax is taking the index as the largest value. The value of the topic, the value of the top topic is the weights of the topic. You want to find the topic with the highest weight, and then simply get the topic index, because the actual weight of the topic, you don't have to care. You just need to find out which topic has the highest weight, the most probable topic for the article. And once you have that, then you can adapt the process from the previous question here. So once you have the topic, I need to get the row terms for this topic. And where do you get this? You get it from the topic words. Topic words to get the words based on the row. You already have the row here. So this is the topics terms in matrix. And by using the index for the top topic, you get the row terms. All right, up to this point, it's new. But then anything following would be these. I would like to print the topic now. So the most probable topic is number topic ID that I identified. And the top words are, these are the top words. Clean a few things that are different to adapt the codes. Row terms are the same, number of top terms are the same, put them to index for the top terms. Feature names are the same. It's actually going to work without any changes here. Okay, so I think that's pretty much it. That completed the 5 or 4 steps, 4 little steps for the for loop. The ultimate output includes the topic, the article index, the most probable topic index, and the top 10, terms of this. Okay, so that's the first part of the exercise. Right, let's see what something did work here. Index 3053 is upper bounds. Okay. I'm probably using a wrong feature name is not index top terms. So let's debug this. If you find where it's wrong, let me know. I'm deviating from my notes because I'm combining multiple steps here. Um, top and term. I think this one didn't print. Oh, it does. Or abstract 0 at most probable topic number 14. The top 10 words are top terms, feature names, really 14 DX. So what is DX top terms? Is this feature names out of bound for axis 0 with size 20? So there is a dimension mixer here that a project is changing probably. It could be feature names is not working because I'm using a wrong data object. It doesn't come from LDA, but count. All right, now it works. So for the first 5 articles, their most probable topic are almost different, but some of them share the same. If the same probable topic is identified, then the top words would definitely be the same because that's under the same topic. Now the first step is the top 10 words is the most likely topic for the article, which essentially is trying to use use the best words to characterize what is being discussed in the abstract. So in a way, you would hope that these top words of the most probable topic would reflect the content of the abstract itself, which means instead of reading the entire abstract here, let me copy, this is the first column, first row of the data set. Instead of reading the whole chunk, 250 words, by looking at here, by looking at the top words, hopefully you get an idea of what the paper is about. So what is this topic? the neurotism, negative anxiety, but there's positive social, there's depression. So some socially driven anxiety and depression, that relates to neurons, something like that. So, socially driven anxiety. But does it actually, and then certainly the topic words doesn't capture the special terms, the APD, the GSP here, that is the top frequency words actually, when we look at the term frequency. So do these words actually capture or reflect what the paper discusses? Not so much, actually. So, socially driven anxiety, but we recognize social phobia. It actually does, there's a social aspect of depression, emerging, but certainly the specific topics that are discussed here, the APD and GSP, are missing from the topic words. So, there's something lost there, but something also gained from the mean instead of the most frequent terms. All right. And the part two here is asking you to simply extract the subject terms in the original data set. And then, you're just going to construct a simple for loop. I'm not going to lay out the logic here for I subjects in enumerate through the DS subjects, I think. And then only the first five rows. Abstract number. I, and then the subject. The author provided subjects for abstract number are simply print the subjects and print the dividers. All right. So it's, APD, comorbidity, social phobia, symptoms, timidity. Those are the subjects provided by, which, maps pretty well with the kind of the subject terms, the special terms that are frequently mentioned in abstract, but somewhat lost in the top words of the topic. But the context is captured, the social aspect, the anxiety are captured. So, there's something gained and something lost. Your conclusion, for the first abstract, the topic words capture mostly the social context of the abstract domain, but the keywords, special terms like APD and GSP are lost. Something is gained, but something else is lost in the top words, right? So, do the same thing when you compare the top topic words with the subjects provided for abstract number 1 and 2 and 3 and 4. Okay, that 5. Now, and then, if you want to attempt a bonus question, do that. It's a natural extension of there's several problems about this, but there are some pointers here. And also limitations that we have found here. The top topic words do not necessarily capture, what the author would like to convey, but it does provide some context, which is latent in the abstract that the author provides. So in order to capture the subjects more likely, how would you, revise the several parameters, such as the, what is it? Such as the meaningful terms, meaningless terms are those terms that happen frequently. So the max DF, how do you change that? How do you revise that in order to capture terms that share more commonality with the subject terms, or that's the overlap terms, and the number of features? Is having more features better or worse in order to improve this aspect of the model? Think about that, and then if you want to attempt, treat it as a fun problem in addition, and try your best and see where you get. Okay, any questions about any of these problems?